Hello everyone, it's a great pleasure for me to be here and present my research topic on vibration and heat-assisted AFM-based nanomachining using probes with different stiffness. Nanomanufacturing refers to the manufacture of nanoscale materials, structures, components, devices, and systems, usually between 1 and 100 nanometer. It has numerous existing and potential applications in technological and biomedical fields. To implement these applications, we have typical nanofabrication techniques, including electron beam lithography, focused iron beam lithography, and AFM-based lithography. Among all the techniques, AFM-based lithography has emerged as an easy-to-set-up and cost-effective machining process with high resolution. AFM is originally used for scanning, but if a larger force is applied on the tip while tip is in contact with the sample surface, it can also be used to generate nanopatterns. However, the direct mechanical scratching of the AFM tip usually requires large normal force, which causes large tip wear. In this study, we implemented a multiple energy-assisted AFM-based nanomachining process. Figure 1 shows a schematic experimental setup. Based on the settings of the original commercially used AFM, we add a heating plate beneath the sample stage to heat the entire sample, and 2 piezoelectric actuators to generate in-plane circular vibration, which is described in Figure 2A and B. If no X5 vibration is applied in the nanomachining process, the change size is going to be the same as the tip size. However, when we apply 2 sine signals with the same frequency, amplitude, and 90-degree phase difference on X and Y piezo, a circular vibration is generated on the sample, and therefore the change size increased. The high-frequency vibration and adjustable amplitude enables high-speed nanofabrication and tunable feature size, while the sample heating technique is applied to soften the polymer and therefore decrease the normal force and extended the tip's lifetime. In this study, we focused on investigating the effect of different types of AFM probes and different heating temperatures on the lithography performance. We conducted a full factorial experiment. There are 2 factors, tip category and sample temperature. The sample we used is silicon substrate spin-coated with 200 nanometer thickness PMMA film. The types of tips we used are in Figure 2C. The first one is TAP 190 DLC. It's a very stiff tip with spring constant 48 Newton per meter. The second one is TAP 150 DLC. This tip also has diamond-like carbon coating. It's wear resistant with spring constant 5 Newton per meter. And the last one is a very soft tip, CSG10 with gold coating. The spring constant is only 0.1 Newton per meter. So there are almost 500 times differences between the spring constant of the stiffest and the softest tip. Figure 3 shows the experimental results, including topography images of the lithography trenches and cross-sectional profiles of the images. We started with the softest tip, with the sample heated up to 35 degrees C. As you can see in Figure 3A, there are no changes showing in the topography image, only some marks on the surface, with hardly any depth. Then we increased the temperature to 42 degrees C and did the same experiment. This time the change depth is around 8 nanometer. The same experiment was repeated using TAP 150 DLC and TAP 190 DLC tips. As you can see in Figure 4A, in the full factorial design experiment, the first factor, tip category, has 3 levels, and the second factor, sample temperature, has 2 levels. Generally, result shows that change depth of the stiffer tip is larger than that of the softer tip for both temperatures. Figure 4b shows the ANOVA table of the factorial experiment, and the p-values of both factors and their interactions are all zero, indicating that the tip category, heating temperature, and their interactions all has significant effect on trench depth. And therefore, we get to the conclusion that other than the setpoint force, the probe category and sample heating temperature significantly affect the dimensions of fabricated nanopatterns, and there is a statistically significant interaction effect between the spring constant of probes and the sample temperatures.